We'll now use that equation we just derived to go back and solve or at least address that same problem we were doing before. So let's write that equation down again. So actually, let's write the problem down. Let's say I have the cliff again, and so my initial distance is 0, but it goes down 500 meters. I'm not going to redraw the cliff because it takes a lot of space up on my limited chalkboard. So we know that the change in distance is equal to minus 500 meters. And I'm going to still use the example where I don't just drop the ball or the penny or whatever I'm throwing off the cliff. I actually throw it straight up. So it's going to go up and slow down from gravity, and then go to 0 velocity and then start accelerating downwards. Or you can even say decelerating in the other direction. But the initial velocity, VI, is equal to, let's say, 30 meters per second. And of course we know that the acceleration is equal to minus 10 meters per second squared. Because acceleration gravity is always pulling downwards or towards the center of our planet. If we wanted to figure out the final velocity, we could have just used the formula, and we did this in the last video. Vf squared is equal to Vi squared plus 2AD. But now what I want to do is see if I'm going to use the formula we learned in the very last video to figure out how long does it take to get to the bottom to hit the ground. So let's use that formula. We derived, and I'll write in a different color. We derived that the change in distance is equal to the initial velocity times time plus acceleration times squared over 2. That's initial velocity. So the change in distance is minus 500. Minus 500 is equal to the initial velocity. Well, that's positive, going upwards, 30 meters per second. 30 t. I'm not going to write the units right now because it'll just make things, I'll run out of space, but you can redo it with the units and see that the units do work out. When you square time, you have to square the time units, etc., although we're solving for time. Plus acceleration. Acceleration is minus 10, but we're going to divide it by 2, right? So it's minus 5. Minus 5 t squared. So we have minus 500 is equal to 30t. We could, plus minus 5t squared. We could just say minus 5t squared to get rid of this plus. So at first you're saying, well, Sal, there's a t that's t to the first, a t to the second. How do I solve this? And hopefully you've taken algebra 2 or algebra 1 in some places, and you remember how to solve this. Otherwise, you're about to learn the quadratic equation. Although I recommend you go back and you learn about factoring in the quadratic equation, which there are videos on that I've put on YouTube. So I hope you watch those first if you don't remember. But what we can do is let's put these two right terms on the left-hand side, and then we'll use the quadratic equation to solve it because I don't think this is easy to factor. So we get 5t squared minus 30t minus 500 is equal to 0. I just took these terms and put them on the left side. And we could divide both sides by 5 just to simplify things. So we get t squared minus 6t minus 100 is equal to 0, right? And I could do that because 0 divided by 5 is just 5, so it just cleaned it up a little bit. So let's use the quadratic equation, and for those of us who need a refresher, I'll write it down. So the roots of any quadratic, and in this case, it's t we're solving for. T will equal negative b plus or minus the square root of b squared minus 4ac over 2a, where a is the coefficient on this term, b is the coefficient on this term, negative 6, and c is the constant, so minus 100. So let's just solve. So we get t is equal to negative b. So negative this term. Well, this term is negative 6, so if we make it a negative, it becomes plus 6. So it becomes 6 plus or minus the square root of b squared, so it's minus 6 squared, 36, minus 4 times a, the coefficient on a is here, that's just 1, times 1, for a c, c is a constant term, minus 100, minus 4 times 1 times minus 100 times minus 100, all of that over 2a. Well, a is 1 again, so all of that over 2. That just equals 6 plus or minus the square root This is minus 4 times minus 100, so these become pluses. So it becomes 36 plus 400, right? So 6 plus or minus 436 divided by 2. And this is not a clean number. And if you type it into your calculator, it's something on the order of about 20.9. We can just say approximately 21. You might want to get the exact number if you're actually doing this on a test or trying to send something to Mars. But for our purposes, I think you'll get the point. So I'll say it approximately now because we're going to be a little off, but just to have clean numbers. This is approximately 21. It's like 20.9. We'll say 6 plus or minus, well, let me just write 20.9. 20.9 over 2. So t is approximately 6. So let me ask you a question. If I do 6 minus 20.9, what do I get? I get a negative number. And does a negative time make sense? No, it does not. That means that somehow in the past, well, I don't want to get philosophical, but the negative time in this context will not make sense. So really, we can just stick to the plus, right? Because 6 minus 20 is negative, so 6 will just, there's only one time that solves this in a meaningful way. So time is approximately equal to 6 plus 20.9, so that's 26.9 over 2. And that equals what? 13.45? 13.45 seconds. Time is equal to. That's interesting. I think if you remember way back, maybe 4 or 5 videos ago, when we first did this problem, we just dropped the penny straight from the height. And actually, in that problem, I gave you the time. I said it took 10 seconds to hit the ground, and we worked backwards to figure out that the cliff was 500 meters high. Now, so if you're at the top of a 500-meter cliff or building and you drop something that has no air resistance, like a penny that has very little air resistance, it would take 10 seconds to reach the ground, assuming all of our assumptions about gravity, whatever. But if you were to throw the penny straight up, off the edge of the cliff at 30 meters per second, right here, it's going to take 13.5, roughly 13.5 seconds to reach the ground. So it takes a little bit longer, and that should make sense because. Actually, I have time to draw a little picture. In the first case, I just took the penny and its motion just went straight down. In the second case, I took the penny, it first went up and then it went down. Right? So it had all the time when it went up, and then it kind of went down a longer distance. So it makes sense that this time is 10 seconds, while this time was 13.45 seconds. So you can kind of say that it took. Well, you actually can't say that. I don't want to get too involved. But hopefully this makes sense to you. If you got a smaller number here, you would have gone and checked your work. Because why would it take less time when I throw the object straight up? So hopefully that gave you a little bit of more intuition, and you really do have in your arsenal now all of the equations and hopefully the intuition you need to solve basic projectile problems. I'll now do probably a couple of more videos where I just do a bunch of problems just to really drive the points home, and then I'll expand these problems to two dimensions and angles, and before we get there you might want to refresh your trigonometry. I'll see you soon.